Is it useful for us to maybe first talk about how quantum mechanics
Let's talk
fits
about quantum mechanics.
into the
Yes.
Wolfram physics model?
Yes.
Let's go there. So we talked about general relativity. Now, what have you found from
What's the story of quantum mechanics? Right.
Within and outside of the Wolfram physics?
Right. So I mean, the key idea of quantum mechanics, the typical interpretation is classical physics says a definite thing happens. Quantum physics says there's this whole set of paths of things that might happen, and we are just observing some overall probability of how those paths work. Okay, so when you think about our hypergraphs and all these little updates that are going on, there's a very remarkable thing to realize, which is if you say, well, which particular sequence of updates should you do? Say, well, it's not really defined. You can do any of a whole collection of possible sequences of updates. Okay, that set of possible sequences of updates defines yet another kind of graph that we call a multiway graph. And a multiway graph just is a graph where at every node there is a choice of several different possible things that could happen. So, for example, you go this way, you go that way. Those are two different edges in the multiway graph. And you're building up this set of possibilities. So actually, like, for example, I just made the multiway graph for tic-tac-toe. Mm-hmm. Okay, so tic-tac-toe, you start off with some board that, is everything is blank, and then somebody can put down an X somewhere, an O somewhere, and then there are different possibilities. At each stage, there are different possibilities. And so you build up this multiway graph of all those possibilities. Now, notice that even in tic-tac-toe, you have the feature that there can be something where you have two different things that happen, and then those branches merge because you end up with the same shape of, the same configuration of the board, even though you got there in two different ways. Mm-hmm. So the thing that's sort of an inevitable feature of our models is that just like quantum mechanics suggests, definite things don't happen. Instead, you get this whole multi-way graph of all these possibilities. Okay, so then the question is, so that's sort of a picture of what's going on. Now you say, okay, well, quantum mechanics has all these features of, all this mathematical structure and so on. How do you get that mathematical structure? Okay, couple of things to say. So quantum mechanics is actually, in a sense, two different theories glued together. Quantum mechanics is the theory of how quantum amplitudes work, that more or less give you the probabilities of things happening. And it's the theory of quantum measurement, which is the theory of how we actually conclude definite things. Because the mathematics just gives you these quantum amplitudes, which are more or less probabilities of things happening, but yet we actually observe definite things in the world. Mm-hmm. Quantum measurement has always been a bit mysterious. It's always been something where people just say, well, the mathematics says this, but then you do a measurement and there are philosophical arguments about what the measurement is, but it's not something where there's a theory of the measurement.
Somebody on Reddit also asked, please ask Stephen to tell his story of the double slit experiment.
Okay. Yeah, I can.
Does that make sense?
Oh yeah, it makes sense. Absolutely makes sense.
Why is this like a good way to discuss?
A little bit. Let me explain a couple of things first. So the structure of quantum mechanics is mathematically quite complicated. One of the features, let's see, well, how to describe this. Okay, so first point is there's this multi-way graph of all these different paths of things that can happen in the world. And the important point is that these, you can have branchings and you can have mergings. Okay, so this property turns out causal invariance is the statement that the number of mergings is equal to the number of branchings.
Yeah.
So in other words, every time there's a branch, eventually there will also be a merge. In other words, every time there were two possibilities for what might have happened, eventually those will merge.
Yeah. Beautiful concept, by the way. But yeah.
So that idea, okay. So then, so that's one thing, and that's closely related to the sort of objectivity in quantum mechanics. The fact that we believe definite things happen, it's because although there are all these different paths, in some sense, because of causal invariance, they all imply the same thing. I'm cheating a little bit in saying that, but that's roughly the essence of what's going on. Okay, next thing to think about is you have this multi-way graph. It has all these different possible things that are happening. Now we ask, this multi-way graph is sort of evolving with time. Over time, it's branching, it's merging, it's doing all these things. Okay. The question we can ask is, if we slice it at a particular time, what do we see? And that slice represents, in a sense, something to do with the state of the universe at a particular time. So in other words, we've got this multiway graph of all these possibilities, and then we're asking, okay, we take this slice. This slice represents, okay, each of these different paths corresponds to a different quantum possibility for what's happening.
Right.
When we take this slice, we're saying, what are the set of quantum possibilities that exist at a particular time?
And when you say slice, are these, you slice the graph and then there's a bunch of leaves?
A bunch of leaves.
And those represent the state of things.
Right. But then, okay, so the important thing that you are quickly picking up on is that what matters is kind of how these leaves are related to each other. So a good way to tell how leaves are related is just to say, on the step before, did they have a common ancestor? So two leaves they might have just branched from one thing, or they might be far away, way far apart in this graph, where to get to a common ancestor, maybe you have to go all the way back to the beginning of the graph, all the way back to the beginning.
So there's some kind of measure of distance.
Right. What you get is by making this slice, we call it branchial space, the space of branches. And in this branchial space, you have a graph that represents the relationships between these quantum states in branchial space. You have this notion of distance in branchial space. Okay, so
it's connected to quantum entanglement.
Yes, yes. It's basically the distance in branchial space is kind of an entanglement distance. So that's
a very nice model.
Right. It is very nice. It's very beautiful. It's so clean. I mean, it's really, and it tells one, okay, so anyway, so then this branchial space has this sort of map of the entanglements between quantum states. So in physical space, we have, you can take, let's say, the causal graph, and we can slice that at a particular time, and then we get this map of how things are laid out in physical space. When we do the same kind of thing, there's a thing called the multiway causal graph, which is the analog of a causal graph for the multiway system. We slice that. We get essentially the relationships between things, not in physical space, but in the space of quantum states. It's like which quantum state is similar to which other quantum state. Okay, so now I think next thing to say is just to mention how quantum measurement works. So quantum measurement has to do with reference frames in branchial space. So measurement in physical space, it matters how we assign spatial position and how we define coordinates in space and time. And that's how we make measurements in ordinary space. Are we making a measurement based on us sitting still here? Are we traveling at half the speed of light and making measurements that way? These are different reference frames in which we're making our measurements. And the relationship between different events and different points in space and time will be different depending on what reference frame we're in. Okay, so then we have this idea of quantum observation frames, which are the analog of reference frames, but in branchial space. And so what happens is, what we realize is that a quantum measurement is the observer is sort of arbitrarily determining this reference frame. The observer is saying, I'm going to understand the world by saying that space and time are coordinatized this way. I'm going to understand the world by saying that quantum states and time are coordinatized in this way. And essentially what happens is that the process of quantum measurement is a process of deciding how you slice up this multiway system in these quantum observation frames. So in a sense, the way the observer enters is by their choice of these quantum observation frames. And what happens is that the observer, this is again another stack of other concepts, but anyway, because the observer is computationally bounded, there is a limit to the type of quantum observation frames that they can construct.
Interesting. Okay, so there's some constraints, some limit on the choice of observation frames.
Right, and by the way, I just want to mention that it's bizarre, but there's a hierarchy of these things. So in thermodynamics, the fact that we believe entropy increases, we believe things get more disordered, is a consequence of the fact that we can't track each individual molecule. If we could track every single molecule, we could run every movie in reverse, so to speak, and we would, we would not see that things are getting more disordered. But it's because we are computationally bounded. We can only look at these big blobs of what all these molecules collectively do, that we think that things are, that we describe it in terms of entropy increasing and so on. And it's the same phenomenon, basically, also a consequence of computational irreducibility that causes us to basically be forced to conclude that definite things happen in the world, even though there's this quantum, this set of all these different quantum processes that are going on. So, I'm skipping a little bit, and but that's a rough picture.
And in the evolution of the Wolfram Physics project, where do you feel we stand on some of the puzzles that are along the way? So you're skipping along a bunch of
it's amazing how much these things are unraveling. I mean, these things, look, it used to be the case that I would agree with Dick Feynman, nobody understands quantum mechanics, including me.
Yeah.
Okay? I'm getting to the point where I think I actually understand quantum mechanics. My exercise, okay, is can I explain quantum mechanics for real at the level of kind of middle school type explanation?
Right.
And I'm getting closer. It's getting there. I'm not quite there. I've tried it a few times, and I realize that there are things that where I have to start talking about elaborate mathematical concepts and so on. But I think, and you've got to realize that it's not self-evident that we can explain, at an intuitively graspable level, something which, about the way the universe works. The universe wasn't built for our understanding, so to speak. But I think then okay. So another important idea is this idea of Branchial space, which I mentioned, this sort of space of quantum states. It is, okay, so I mentioned Einstein's equations describing, the effect of mass and energy on trajectories of particles, on geodesics. Mm-hmm. The curvature of physical space is associated with the presence of energy according to Einstein's equations. Okay, so it turns out that, rather amazingly, the same thing is true in Branchial space. So it turns out the presence of energy, or more accurately, Lagrangian density, which is a kind of relativistic invariant version of energy, the presence of that causes essentially deflection of geodesics in this Branchial space. Okay, so you might say, so what? Well, it turns out that the best formulation we have of quantum mechanics, the Feynman path integral, is a thing that describes quantum processes in terms of mathematics that can be interpreted as, well, in quantum mechanics, the big thing is you get these quantum amplitudes, which are complex numbers that represent, when you combine them together, represent probabilities of things happening. Mm-hmm. And so the big story has been, how do you derive these quantum amplitudes? And people think these quantum amplitudes, they have a complex number, has, real part and imaginary part. You can also think of it having a magnitude and a phase. And people have sort of thought these quantum amplitudes have magnitude and phase, and you compute those together. Turns out that the magnitude and the phase come from completely different places. The magnitude comes, okay, so how do you compute things in quantum mechanics? Roughly, I'm telling you, I'm getting there to be able to do this at a middle school level, but I'm not there yet. The roughly what happens is you're asking, does this state in quantum mechanics evolve to this other state in quantum mechanics? Mm-hmm. And you can think about that like a particle traveling, or something traveling through physical space, but instead it's traveling through Branchial space. Mm-hmm. And so what's happening is, does this quantum state evolve to this other quantum state? It's like saying, does this object move from this place in space to this other place in space? Okay. Now, the way that these quantum amplitudes characterize kind of to what extent the thing will successfully reach some particular point in Branchial space. Just like in physical space, you could say, oh, it had a certain velocity and it went in this direction. In Branchial space, there's a similar kind of concept.
Is there a nice way to visualize, for me now, mentally, Branchial space?
It's just, you have this hypergraph, you have this multiway graph. It's this big branching and merging thing.
But I mean, moving through that space. I'm just trying to understand what that looks like.
Space is probably exponential dimensional, which right. makes it, again, another can of worms in understanding what's going on. That space, as in ordinary space, this hypergraph, the spatial hypergraph, limits to something which is like a manifold, like something like three-dimensional space. Almost certainly, the multiway graph limits to a Hilbert space, which is something that, I mean, it's just a weirder exponential dimensional space. And by the way, you can ask, I mean, there are much weirder things that go on. For example, one of the things I've been interested in is the expansion of the universe in Branchial space. So we know the universe is expanding in physical space, but the universe is probably also expanding in Branchial space. So that means the number of quantum states of the universe is increasing with time.
The diameter of the thing is growing.
Right. So that means that and by the way, this is related to whether quantum computing can ever work.
Why?
Okay, so let me explain why. So let's talk about. Okay, so first of all, just to finish the thought about quantum amplitudes, the incredibly beautiful thing. I'm just very excited about this. The Feynman path integral is this formula. It says that the amplitude, the quantum amplitude, is e to the I s over h bar, where s is this thing called the action, and okay, so that can be thought of as representing a deflection of the angle of this path in the multiway graph. So it's a deflection of a geodesic in the multiway path that is caused by this thing called the action, which is essentially associated with energy. Okay, and so this is a deflection of a path in Branchial space that is described by this path integral, which is the thing that is the mathematical essence of quantum mechanics. Turns out that deflection is the deflection of geodesics in Branchial space follows the exact same mathematical setup as the deflection of geodesics in physical space, except the deflection of geodesics in physical space is described with Einstein's equations. The deflection of geodesics in Branchial space is defined by the Feynman path integral, and they are the same. In other words, they are mathematically the same. So that means that general relativity is a story of essentially motion in physical space. Quantum mechanics is a story of essentially motion in Branchial space. And the underlying equation for those two things, although it's presented differently because one's interested in different things in Branchial space than in physical space, but the underlying equation is the same. So in other words, it's just, these two theories, which are the two sort of pillars of 20th century physics, which have seemed to be off in different directions, are actually facets of the exact same theory. And this,
that's exciting to see where that evolves, and exciting that just is there.
Right. I mean, to me, look, having spent some part of my early life, working in the context of these theories of 20th century physics, they seem so different, and the fact that they're really the same is just really amazing. Actually, you mentioned double slit experiment. Okay, so the double slit experiment is an interference phenomenon where you say there are, you can have a photon or an electron, and you say there are these two slits. It could have gone through either one, but there is this interference pattern where there's destructive interference, where you might have said in classical physics, oh, well, if there are two slits, then there's a better chance that it gets through one or the other of them. But in quantum mechanics, there's this phenomenon of destructive interference. That means that even though there are two slits, two can lead to nothing, as opposed to two leading to more than for example, one slit. And in what happens in this model, and we've just been understanding this in the last few weeks, actually, is that what essentially happens is that the double slit experiment is a story of the interface between Branchial space and physical space. And what's essentially happening is that the destructive interference is the result of the two possible paths associated with photons going through those two slits winding up at opposite ends of Branchial space. And so that's why there's sort of nothing there when you look at it, is because these two different sort of branches couldn't get merged together to produce something that you can measure in physical space.
Is there a lot to be understood about Branchial space? Like,
yes,
mathematically speaking?
Yes, it's a very beautiful mathematical thing. And it's by the way, this whole theory is just amazingly rich in terms of the mathematics that it says should exist. Okay, so for example, calculus, is the story of infinitesimal change in integer dimensional space, one-dimensional, two-dimensional, three-dimensional space. we need a theory of infinitesimal change in fractional dimensional and dynamic dimensional space. No such theory exists.
So there's tools of mathematics that are needed here.
Right.
And this is a motivation for that, actually.
Right. And it's there are indications, and we can do computer experiments and we can see how it's going to come out, but we need to, the actual mathematics doesn't exist. And in branchial space, it's actually even worse. There's even more sort of layers of mathematics that are, we can see how it works roughly by doing computer experiments, but to really understand it, we need more sort of mathematical sophistication.